Thank you very much. It's a great pleasure to be here. I'll be talking about a sort of hardware application or experimental system, and in particular, an experiment that we've conducted in Chris Monroe's group here at the University of Maryland, where a trapped ion experiment constitutes a programmable quantum computer. And our recent efforts have been focused on topics related to machine learning, which is of course relevant to what I've heard so far in this conference. And so I'll tell you briefly about what we've been doing. I'll start by saying, since some of you may not be familiar with our experimental platform, why it is a good idea to use ions as the basis for a quantum computer. And then I'll present our hardware and how it constitutes a quantum computer. And then I'll give 4 recent examples, which are sort of, most of them are actually still ongoing works that are related to machine learning. Okay, so to get started, if you want to build a quantum computer, you need some kind of pristine quantum system under your control, and a single atom isolated from the rest of the universe is kind of a very good place to start. There are energy levels in atoms, which you can use as your qubit states, and you can sort of interact with these atoms using laser light. Typically, these are sort of in the optical regime, which means you don't have to necessarily cool your experiment down very far to avoid excitation from background radiation, and you can detect fluorescence from these atoms to learn something about their state. Now, what's particularly nice about atoms is that they are standards. Every atom of a given species is identical, so you can scale this system by adding more atoms, and they'll all be identical in your system. So now there's a little bit of a conundrum. On the one hand, we want these nice pristine systems that don't decohere very much, so they shouldn't couple to their environment. But on the other hand, we want to drive some kind of quantum gate, so we need them to interact with each other very strongly. And here ions are particularly useful because they are, of course, charged atoms, which means they interact with each other via the Coulomb interaction. And if you trap several of them in a common trap potential, they will show motional modes, which are basically quantum harmonic oscillator modes that you can use to create entangling gates between them. So this is kind of the grand vision for ion-trapped quantum computing. You have some kind of device that traps many ions. You can move them around, you can entangle any of them and build a larger computation. And of course, this is not going to be infinitely large, so you might consider this a single module in a bigger system where these modules are connected by entangled photons. And of course, we're not there yet. We're working on several technological challenges, mostly increasing the control over the system, controlling more qubits, more ions, and improving the fidelity of our quantum operations. Note that qubit quality is not one of the points here, and that's because they're basically atomic clocks and are sort of perfect by nature. What's imperfect, where all the errors come from in this case, is really our imperfect control and our sort of limited control during our gate operations. Okay, so how does ion trapping work in practice? Imagine a electric field. This is a quadrupole, and this is a positively charged particle. If this was a static quadrupole, of course, it would just be attracted by one of these negative electrodes. So what we do is we change the polarity of this quadrupole reasonably fast, such that the particle is dynamically trapped in 2 dimensions. I don't know if you can see this in the back. Contrast is a bit low. And then in the third direction, we just add a static electric potential, and that allows us to confine individual ions in all 3 dimensions. And here you can see a little movie of a single ion sitting there, basically suspended in free space and ready to be manipulated and experimented on. And so this is kind of the most basic trap geometry, but there are many more that have been developed in recent years. Also, this geometry can be folded into a single plane with additional control elements such as microwave electrodes, waveguides, and so on integrated. So there's been a lot of progress in this technology recently. Our current trap, that's in the basement of this building, looks like this. You can see these 4 blade-like electrodes that make the quadrupole. And then here, there are some sort of segments that we can use to add the static field in this axial direction. This whole thing is about 1.5 inches long. And it allows us to reliably trap small numbers of individual ions. And that's kind of the basis for our quantum computer. Each of these little dots that you see here is a single ytterbium-171 ion, and these are the energy levels. And most of them you can ignore. The main ones are these 2 down here, 0 and 1. This is our qubit. And they have the nice property of having magnetic field quantum number 0, which means to first order they're insensitive to changes in the magnetic field. And that means without trying very hard, we get coherence times in excess of a second. So our most recent measurement is 1.5 seconds in the system, which you can extend, of course, if you were to shield the magnetic field or if you were to use some sort of compensating pulses to reduce this kind of decoherence. So I think the record is 10 minutes in this system of coherence time that has been measured. This transition here is also relevant, 370 nanometers. This is what we use to initialize and detect our qubit state. And I'll very briefly mention how that works. So in the beginning, we're going to be starting in some random state down here, and we're going to send in a particular frequency of this 369 light, such that we depopulate these three states up here and initialize to state 0. What we then need is a way to detect at the end of a computation if we're in state 0 or in state 1, and we do this by state-dependent fluorescence. So if we're in state 1 and we send in laser light of this particular transition, we have a cycling transition between these two states, and because of selection rules, this state does not decay to 0, and that means if the ion is in state 1, it'll scatter many photons. If it is in state 0, it'll stay dark, and we can discriminate between the two by just counting photons for a certain amount of time, and then deciding how many photons we have. If we have 0 or 1, we call it dark. If we have more, we call it bright, and that way we can read out our qubit with a reasonably high fidelity. Okay, so now we know how to initialize and read out. We need some way of manipulating our qubits, of driving gates, and we do this by driving a Raman transition. We basically send in two laser beams that are off resonant from any of these upper levels, but are detuned from each other by exactly the qubit splitting of 12 gigahertz. And we achieve this with a laser that's a pulsed laser. Basically, it's a frequency comb, and we shift these two beams with respect to each other such that the different comb teeth here interfere to give you exactly a beat note at that frequency. And that's kind of the basis for all our single and two qubit gates. Okay, so that's all of the basic ingredients. And now I'm going to take a sort of systems view, and I'm going to present an architecture, if you like. So this is what a computer scientist would call the stack. You're trying to run some algorithm. In the present case, this would be some kind of machine learning relevant application, which comes to you as a circuit that's written down as standard computational gates, which you can break down into your native gates, which you then apply as some kind of laser pulse shapes on your actual physical hardware. And so I'll very briefly mention each of these stages, starting at the bottom here with the actual hardware. So this is a sketch of what our system looks like. The trap itself is not shown. Each of these little dots in the center is a ytterbium ion. So currently we work with 7, and here there's 5 in this picture. And we apply these Raman beams that I presented on the previous slide in the following way. There's one beam from the back, which illuminates the entire chain. And there's one from the front here, which is split up into many beams, goes through an acousto-optic modulator, which is then imaged onto the ions. And these beams each have their own controller in this device, and that means we can switch them individually, and we can control the amplitude, frequency, and phase of each of these separately, and each beam just hits exactly one ion. And that means we have a lot of control over these individual quantum systems. So for detection, we image this ion chain onto a multi-channel photomultiplier. So there's many detectors here in this device, and each ion is imaged exactly onto one. So here you can see channel number versus photon counts, and you can see this is the chain of 5 ions here. And that means after a computation, we can tell exactly for each ion whether it is bright or dark, and we can tell which of the 2 to the n output states we have, with some readout error, of course, which I'll come to later. Okay, so that's the lowest layer. Then I'll come to our native gates in the system. And there's 2 types, R gates, individual rotations, and entangling gates. So individual rotations are just that. It's basically Rabi flopping between these 2 qubit states. And we have control over the duration of the pulse and of the phase of the pulse. And that allows us to do a rotation on the Bloch sphere by an arbitrary angle around an axis that's anywhere in the XY plane of the Bloch sphere. And this is a way of describing this as a unitary. More interestingly, we can do entangling operations. And for that, as I mentioned before, we use the motional modes. So if we tune our beams to resonance, we get these Rabi flops that I showed on the previous slide. but if we detune by a motional mode frequency, which in our case is about 3 megahertz, we get these sidebands. So these transitions correspond to flipping the spin or changing the qubit state and adding motion to the harmonic oscillator modes, and these correspond to flipping the spin and removing a quantum of motion from these oscillator modes. And if we send in light near the blue and red sideband simultaneously, you get a unitary that looks like this. There's a spin-motion interaction and a spin-spin term, and if we engineer our pulse just right, we can null this term out, basically leaving the motion disentangled from the spin at the end of the gate, and we are left with a pure spin-spin entanglement term. And so if we successfully do this, we pre-calculate what that pulse is, and we play it back, we can end up with a maximally entangling gate, which has a parameter here, which sort of is the envelope of that pulse. And if we set that parameter to the right value, we can generate a maximally entangling Bell state. Now the key is all the ions participate in the motion, of course, but only the ions that have the laser beam applied to them participate in the spin evolution. And that means we selectively entangle exactly 2 ions out of this chain of n ions. And since we can apply this scheme to any 2, this constitutes a fully connected quantum system. So each of these gray lines here is a gate that we can apply. And you can see there's n choose 2 connections, in this case 10 in a 5-qubit chain. Okay. Now how do we make this into computational gates? For this we have a compiler, and obviously this is a computer science conference, so this is, I have to say, probably the most primitive version of a compiler you can imagine. It's essentially a lookup table which tells you if you want to do, let's say, a CNOT gate, how does that CNOT gate break down into the individual rotations and entangling gates that I presented on the previous 2 slides. And so if you want to invoke this controlled NOT gate, the compiler is going to look up this circuit as well as some calibration parameters that go in here, and we'll then be able to play back this CNOT gate, which you can then access from sort of a higher level programming language. You tell it CNOT and it knows exactly what pulses to do. And in a 5-ion chain, there's going to be 10 different CNOTs. Here's some data for all of them. This is a couple of years old, so we recently improved our fidelity a little bit. We can do a CNOT with about 99% fidelity. Okay, I think this is sort of all the ingredients here. And now we can come to different applications. I don't know if there's any questions up to this point. All right, so over the past couple of years, we've run quite a few different algorithms and ideas on the system. Here's a sort of incomplete list, so if you're interested in any of those, you can find me later. There's quite a few related to machine learning. This one and this one, as well as this one with Alireza from QuICS here, which I'm going to talk about. There's also a new one, which I'll be mentioning briefly at the end, which is about QAOA. And so I'll be starting on those examples. I'll start with this one. So I should maybe say one thing, which is that this is a quantum machine learning conference, and some of these results may or may not meet your definition of quantum machine learning. They definitely have to do with a quantum computer, and they have to do with machine learning. And so I'm happy to debate or hear your opinions, which of these examples actually qualify to be included. Okay, I'll start with something I would call machine learning for a quantum computer. And this goes back to this readout problem I presented earlier, which is that we collect photons from these ions for a certain amount of time, and based on those photons, on that photon number, we have to decide, is the ion or the qubit in state 0 or in state 1? Okay, and I showed you this graph before cheekily on a linear scale, so it looked very nice, but if you put it on a log plot, you can see there's quite a big overlap here between the 2 different states. And so the question is, can you do better? Instead of doing some kind of fixed discriminator, can you do better by employing machine learning? And it turns out you can. So the issue is the following. You have ions here, and you image them onto channels. Okay? And if you take this data and use a machine learning scheme to classify it, how much better can you do? Additionally, maybe I should say this first. What I've presented here is sort of a fixed window. We just collect photons for 150 microseconds, and then we decide. But you might actually, get more information out of the system. For example, you can record the arrival time of each of the photons, and that gives you additional information from the system that it's hard to incorporate just from a simple scheme like this. But if you have a machine learning-based approach, maybe that the information contained in that additional sort of arrival time can be incorporated without having a precise model of how that works, but maybe you can just learn how that relates to the different states. And here you can see some sort of example data. This is for 3 qubits, all zeros to all ones. And here's in sort of interrogation time or detection time or readout time. Darker just means more photon counts. If you ignore these timestamps, you can just look at the integrated values over here. Additionally, this detector has many more channels than ions. So you might map the ions onto channels that are, here you can see it well, that are not adjacent. So you have some empty channels in between the ion channels, okay? And that might additionally give you some information about what's going on, okay? And so in order to help us classify this, we used an artificial neural net, which means there's some input layers, some hidden layers, and an output layer. So this is basically photon counts and arrival times, and this is qubit state. And so we took some training data, optimized this neural net, and then used some separate data to see how well it performs. And so we used several different methods to compare how this works. So this is for 3 qubits. FT means fixed threshold. It just means the very simple method of deciding this many counts means bright and this many means dark. Adaptive threshold means you look at what the neighbors are doing to maybe infer a little bit about the crosstalk. NN means neural net. So you can see the fidelity is a little bit higher. NN plus means neural net incorporating the additional empty channels between ions. TNN means neural net incorporating the arrival times of the photons. And TNN plus means incorporating both. And you can see as you add more features to this neural net, as you give it more information and let it learn, let it digest more of these, it's getting better and better at classifying these results. And you can see that this is the error, which is here about 3%, goes down by about 1/3 by letting the neural net apply these additional pieces of information. Okay, the improvement, in absolute fidelity terms, is not terribly high, but that's because our fidelity is already pretty good. So we're already making pretty good use of our information. So we did something else, which was use 5 ions and squeeze them together so that they are really on neighboring channels, right? 5 channels and 5 ions, so there's no pluses here. And so the fidelity is a lot worse. Yeah? And here you can see, again, the boost that you get from adding additional features using the neural net and the neural net with timing information, again, improving the fidelity by a little more than a factor, a little more than 1/3, or reducing the error by a little more than 1/3. Okay, so this is, I would say, machine learning to improve your quantum computer, if you like. One other question we tried to answer was, what is does this neural net actually learn a mechanism that corresponds to what we expect to happen in the physical system? And so here's a different type of neural net called a recurrent neural net, where instead of just feeding it the whole information, you feed it sort of one by one. So you have the different nodes, and you add the information of the different time intervals bit by bit, and you teach it that way to classify the different qubit states. And that way you can sort of change the length of this recurrent net and see how that influences the fidelity. And that's this curve. Here you can see that as we make the detection time longer, the fidelity goes up, which is kind of what you expect, and it also flattens out. So detecting for a longer time is not going to help you anymore. Additionally, once we have trained this, we can sort of feed it some artificial data and map out what its internal mechanism is. So we took a single photon count and we just shifted its arrival time and let it tell us what it thinks the probability that this comes from a bright ion or from an ion in state 1 is. And you can see the later the photon arrives, the less likely, this is the right axis, the less likely it is that this comes from a bright ion. When the photon arrives very late in the detection window, it probably comes from maybe a background scatter or a dark count in the detector. Okay, and so that tells us that what this neural net has learned actually sort of is an image of what we think is actually happening in the system. Okay, so that's machine learning based readout, I would say. The next example, maybe I should wait if there's any questions. Also, I should look at the time roughly. No, we're okay. So the next example has to do with nuclear physics. And so this is I guess, related to some of the chemistry problems that were mentioned by the previous speaker. And this has to do with finding the binding energy of the deuteron nucleus. So deuteron nucleus is a proton and a neutron. And can we use a quantum computer to calculate the binding energy of this nuclear system? The official value for this is minus 2.2 MeV. And you can using an effective field theory, you can map this problem to a number of qubits. So if you use 3 qubits, you obviously lose some granularity or some precision in the problem, and theoretically you should be able to find this number by using this sort of simplified 3-qubit Hamiltonian. And if you map this to a circuit, this is what it looks like. The idea is then you run this circuit on a 3-qubit system and you measure the energy by evaluating the expectation value of this Hamiltonian. And then you vary these parameters here, eta and theta, in order to find the minimum binding energy. And if you map this circuit to our gates, this is what it looks like. You can see 3 entangling gates, some individual rotations, and many of these gates have these parameters in eta and theta. Okay. Now, I'm very grateful for the previous speaker, actually, Kristen. I don't know if he's still here. I guess not. Okay, so he presented a very important concept, which was error mitigation, which is that if you're trying to evaluate the expectation value of a circuit, even a short circuit, you will be plagued by errors in all of these different gates. Okay? And so what he presented is a way to mitigate these errors by increasing the noise and extrapolating to a smaller noise result. And so the way he presented this is to extend the sort of pulse time, I guess. This was sort of in the context of his superconducting system to increase the noise. This, of course, doesn't directly map to ions, because if we do these gates slower, actually our error goes down. So we decided not to do that, and that's because we're not limited by coherence time, right? We decided to do this differently. We decided instead of doing these gates slower, we would do these gates several times. So instead of doing this gate once, we could do it once plus, we could do it 3 times, where the last 2 times sort of cancel each other out in terms of their action on the qubits. Okay, so the idea would be you do a noisy identity after each of these entangling gates. These entangling gates are the main source of error in our system. That's what I should probably be adding. And so the idea is we run this circuit once, and then we run it again, adding additional noise gates after each entangling gate, and then more noise gates and so on. And here you can see our data. This is the data from the IBM system running the same problem. And this black line here is the energy. These other colors are just the different terms in the Hamiltonian. And you can see this is if we run each gate once, if we run it 3 times, 5 times, and 7 times. This is, of course, odd numbers because we always add 2 more gates, right? 1 gate forward and 1 backwards, so that the circuit is effectively the same, but the noise goes up. And this is the extrapolation or zero noise extrapolation that the previous speaker, whose paper is here, has just presented. And you can see it works well, just as he explained, to give us an error that's pretty close to the actual value. Okay, so what we would like to do, of course, is to see if we can get to a better, get closer by increasing the size of the qubit space that we're actually using. So this is the same Hamiltonian mapped to 4 qubits. You can see the energy is closer to the real value, and this is the circuit. Now, of course, there's more parameters here. No, actually, there's not. There's 2 parameters here, but there's more gates here. Yeah, there's 1 more parameter here. Sorry, here, phi. There is more. I overlooked that. There are 3 parameters here, but there's more gates, crucially. Okay, so this is just a longer circuit that corresponds to one of these blocks. Okay, and so here's data from that experiment using again 1, 3, 5, and 7 gates, and extrapolating down, and we're actually very close to the actual exact value for the deuteron. And so this, of course, was done using the values that we're sort of expecting to be the correct values. So we didn't really do any machine learning as such. What you'd really like to do is to start at random values and then learn exactly what the best parameters are to get to this point and then extrapolate to 0. And so to do this, we've investigated a little bit what the parameter landscape looks like for these 3 parameters on the previous slide. And so here you can see that this is actually a pretty smooth variation. So this is the, sorry, this is a bit small, the expectation value. And you can see this is a minimum that actually is pretty close to the minimum for all parameters. So something like a gradient descent should probably work well for this system. We've also explored this experimentally, but I haven't gotten the data yet. So I would say the next step along these lines would be to take a Hamiltonian and learn some unknown parameters that will then give you the right answer for one of these chemistry or nuclear physics problems. Okay. Any questions about this? Ah, you're back. Good. No, I just talked about your extrapolation method here, which actually worked very well on our system. Yes.
Can you do higher order extrapolation since you're not limited to?
You mean if you add more gates or something, or like I would say increase the number of gates in a non-linear way?
Can you go beyond 7?
Yes, I guess we could go beyond 7. In principle, let me just see. This means you add 7 to each gate here. So there's 1, 2, 3, 4, 5. That would be, we're already doing 35 gates. So the limits what we can do on our experiment is currently around that number, so in the 30s, which is pretty good. But there's some sort of technical issues, I would say. We have to upgrade our experiment to go longer. This is not an ion issue. This is a controller issue, unfortunately. But in principle, yes. I mean, it would be kind of nice to see. I mean, at some point, this is probably going to stop being linear.
We need higher order cloud-fitting, but that made it worse. Right?
Yeah, so that's right. So we try to fit to, but it's only 4 points. So this is why it's a bit, shaky to just do like higher order extrapolation here. But we find for these sort of small systems, this linear extrapolation actually works pretty well. Okay. Yes, okay, so now I'll move on to something where some actual learning took place. And this is what we call the bars and stripes problem. So these are sort of 6 different patterns here corresponding to bars and stripes. And we are going to assign each of these to a particular state in a 4-qubit system. In general, it's going to be an entangled state. And our goal is to prepare a state that is an equal superposition of all these 6 different states. So that's our goal here, this state. And we're going to get to this goal by using a circuit that has different layers of gates, single qubit, 2-qubit, and so on. And these have different parameters. And we're going to start by guessing some parameters, evaluating the circuit, getting the outcome, and then sort of using KL divergence, evaluating the mismatch or match between those 2 distributions. That gives us a cost function based on which we can update the parameters and so on, and learn how to prepare the state, essentially. So this is sort of what we expect to get. So if we put in the theoretically correct values, we can see we can get those states. We tried this using a star connectivity, so restricting ourselves to these 3 gates, which means the optimum is not perfect. There's these 2 extra states here which we can't get rid of. But if we add some connectivity, if we add more gates here, you can actually prepare this state pretty well. And the same is true for a instead of 2 layers, doing 4 layers of gates. We can get pretty close to what we want. Now, the question is, how do we update this function, right? So we need some way of, I guess some learning process or some optimization process. And here we made a choice, which is maybe, I'm happy to hear your opinions on it. We chose particle swarm optimization, which basically works like this. You have a bunch of particles. This is parameter space. You start with a bunch of either random or in a certain structure assigned values, and they're each going to start moving around, and they're going to be attracted by positions in their history that was better than their current position, as well as their friends who have a better score than they do. And so some of them will get stuck out in the weeds here, but the idea is a few will actually end up in the global optimum. Okay, so now how did this work? This is the star layer connectivity. So this is 3 different gates. One layer single and 1 layer 2-qubit gates. This is the cost function starting at a random value, and then it sort of converges down here. And once you are here and it flattens out, you can look at what you have, what's your best particle here, and it turns out it's actually pretty close to the actual state that you're trying to learn. So this is the state we want. This is the state we got. So it converged to the right value, basically. So that's for the 2-layer star. So that's this guy. Now let's try this one. This one we should get actually only 6 states out. There's a few more parameters. So we had a few more particles to evaluate at every step. And I have to say, so here you can see it also converges, which is great, but it didn't converge for all random variables. So we actually had to try quite a few different sort of guesses in the beginning in order to get this to converge. Once you find one that converges, though, you get a state that is actually, again, matches the state that you want pretty closely. Okay. So now, you know, this was easier, this was easy, this was harder. So how about this one? This one down here, you can see this has nearly double the number of parameters. And so here I would say this is really where you can see the disadvantage of this particle swarm, because it is kind of wasteful in the thing that's costly for us, which is function evaluations. So the thing that takes time is actually running the thing on the quantum computer. And so if you have a lot of parameters, you'll need a lot of particles to be able to cover this space. And most of them won't actually succeed. And that means it's going to be a very sort of costly enterprise. And so trying this actually has not worked. So we're working on trying to use something different than particle swarm. But with these, you know, with the method that we've been using for the smaller systems, we actually couldn't get it to converge. So, you know, again, happy to discuss options for the systems. You probably have some ideas. Okay, so I'll just say we're currently working on a Bayesian approach where the choices you make are a lot less random than in the particle swarm, where basically you're trying to sort of optimally use the information you've gathered so far to make a choice about what parameters to try next. Okay. Any questions about this? Okay, so then let me just check my time. Okay. Yes, I'll move on to sort of the last application, which is QAOA, quantum approximate optimization algorithm, or, as I've learned earlier, quantum alternating operator ansatz. So the idea here is you're trying to find a certain ground state of a certain Hamiltonian. In our case, we chose the transverse field Ising Hamiltonian, so you have some interaction term, you have some transverse field term, and you're trying to find the ground state for certain values, right? And so one way you could do this is to just prepare the ground state of one sub-Hamiltonian, let's say this one, and then you adiabatically turn on this guy, and you sort of stay in the ground state, which of course gets harder and harder if you have smaller energy gaps or larger systems. And so the idea here is you don't do this adiabatically at all. You do a sort of bang-bang approach. You just apply these two Hamiltonians alternatingly, and you apply them with different parameters. And then you're trying to find the minimum energy to get to that sort of ground state. And so here's an example for depth 2. You start in some eigenstate of one of them, and then you just hit it with the two Hamiltonians alternatingly, and you have some parameters here that you can tweak to find the optimum. And your cost function, of course, is the energy of that state with respect to that Hamiltonian. Okay. Yes, so we chose a sort of nearest neighbor Ising Hamiltonian. So these XX are nearest neighbor. And it's a circular boundary condition. So you can see there's entangling gates here and connecting the edges. So that's 6 gates. And then this is a series of single qubit gates. And they have parameters A and B. And if you do up to 3 of these blocks, you can get the exact value out. And if you do fewer of them, then you have to sort of take a hit in terms of your precision that you can achieve. And so we've done this with p equals 2 and p equals 1. With p equals 2, so running this block twice, we were curious if we start at the sort of ideal values, will the system actually improve? So the way to optimize here was a gradient descent. So at every point, we would sort of explore each of the parameters, just try a sort of offset on each of the parameters to evaluate the gradient, and then walk in that direction. And so this is for p equals 2, starting from the theoretical optimum. And you can see things don't really move very much, and the system essentially stays where it is. This is the energy or the cost function, the black line. And again, let me see. And the theoretical optimum here is about minus 8.1. And we stay away from that because of experimental error, and that doesn't really help with by sort of exploring the space. So we're essentially dominated here by noise in the gates or fluctuations, rather than limited by the coarseness of this QAOA approach. Okay, So then we thought, what about maybe we get a better result if we start not with p equals 2, but with p equals 1. And here we were able to actually start from a random seed and learn these parameters. And you can see here, we started with some value for both parameters, then iterated, evaluating the gradient at every point. So the black point is the energy, and these here are probes, which means it's the same circuit except varying one of the parameters in one direction. If it gets higher, you should go one way. If it goes lower, you should go the other way. And so then we evolved this, and after 10 iterations, we stopped, and the value that we get is around -8, which is closer than the value for p equals 2, which means the coarseness of the QAOA is not the dominating factor. The gate errors are kind of what's keeping us from reaching the optimum. Okay, but this is kind of another application, all of it sort of following the same theme, I guess, which is you're trying to do something on the quantum computer, which is evaluating some function, some Hamiltonian, and you're using a classical optimizer to choose the parameters and get you to where you want to go. And sort of what we've been finding, maybe to you this is of course no surprise, is that the classical optimizer tends to be, especially for these small problems, tends to be one of the hard choices in getting good results. And using some of these NISQ techniques that the previous speaker mentioned is actually also very helpful in improving the estimation of these expectation values. Okay, any questions about this? I'll be moving on to a little outlook after this slide. So, okay, so this is of course a 7-qubit quantum computer. So how do we intend to increase the system? So we can of course add more ions to our trap, but at some point there's going to be a trade-off there. As you increase the number of ions, it's going to be harder and harder to do gates between, let's say, ions on one end to the other end. So there might be a point at which it might be more advantageous to have groups of ions. And since they're trapped with electric fields, we can actually move these around in real space and have fully connected groups on one end, maybe move some of them and have a fully connected group over here. That means the overall system won't be fully connected, but it'll still be pretty densely connected. And then maybe you connect this kind of module using entangled photons to another module. But then you end up with something that I call the compilation challenge. So I presented to you the most primitive version of a compiler you can think of, which is a lookup table. But this compiler that maps a circuit to this kind of architecture will have to make quite a few choices. Right? It'll have to choose when to split up, where to split up, where to move, when to ask for this resource, and all of which have sort of costs associated. And so I hope we don't need a quantum computer to program our quantum computer. The good news is we don't need to find the global optimum. We need to find something that works. And I think here, machine learning is going to have a big role to play in terms of optimizing these operations. And currently, we have another project with Alireza and Paraj, who are in the audience, which has to do with gate learning. Could you maybe use your machine learning technique to optimize your calibration and your routing, essentially, in your quantum computer? And I think these are kind of important questions to address in the near term, because we're going to be in this situation pretty soon in the next few years. Okay, with that, I'll say one more thing, which is the next version of our experiment. We're trying to go beyond 7, of course. So I showed you our sort of our trap with 4 blades. Here's sort of the state of the art in ion trapping, which is a chip trap made by Sandia National Labs. Which is embedded in an experiment that is engineered in a much more professional way than our current system, and boxed up, more stable, and so on. And that's currently being developed by these people in Chris's group, and it also forms the basis of Chris's company IonQ. And so we are hoping that in the next half a year to a year, we'll be able to do these kinds of algorithms on a system of 15 to 20 qubits rather than 5 to 7. Okay, with that, I'll thank everyone involved. These are the people who built the programmable quantum computer. Shantanu and Caroline have now left. We have 2 new students, Cynthia and Nyung, in the lab, who are not pictured here. Especially Daiwei and Kevin were involved in taking data for these quantum machine learning applications, which are still going on. And then this is a list of all the collaborators that were involved in these machine learning projects. Alireza and his supervisor Mohammed for the machine learning assisted readout, Marcello Benedetti and Alejandro Perdomo Ortiz, who came up with the bars and stripe method, and Sonika and Tim for QAOA and Shihab and Nam at IonQ, who helped us with the Deuteron circuit and Deuteron simulations. Thank you very much.
Any further questions? Could you go back to the slide where you used machine learning and neural networks to distinguish between
Yeah.
0 and 1 states? So my question is, how do you say, like, if the error is in the state preparation or if it's because of the like the machine learning?
Yeah, that's right. I didn't talk about this at all. How do we get this data? How do we get the training data, and how do we evaluate it? And so the way we do this is by actually not using 3 ions, but instead we are using 1 ion, and we're moving it into the place of the 3 ions. And that will basically allow us to avoid any kind of addressing error during state preparation of these states. And the preparation of this, if we were to do this with our addressed Raman beams, we'd have addressing crosstalk, and we have some limited fidelity in terms of preparing a 1 state, let's say. And so we use a single ion and we use a microwave pulse. And these microwave gates are obviously much slower, but they have very high fidelity. And so, of course, we still have some preparation error, and we have some other error that comes from adding this data up for 3 individual ions. But all of these are much smaller than the actual readout error, which is about 1 to 0.5% per ion. And these preparation errors are more below 0.1.
What's the physical limit for ion trap to get better fidelity, and why is ion trap have better fidelity than other methods like neutral atoms?
Compared to neutral atoms, I'd say that the strength here is that we have this strong coupling using the Coulomb interaction. So that means we have a very sort of strong and robust gate mechanism. What limits our fidelities essentially is technical things like intensity noise seen by the ions. So this could be the intensity of the laser fluctuating, or the beam's position fluctuating with respect to the ions. And that means that during a gate, we don't really do this pulse shape perfectly that we pre-calculated, and that means we are going to be slightly entangled with these harmonic oscillator modes, with these motional modes at the end of the gate. And of course, we don't measure them, that we sort of trace over them, and that means we have a little bit of mixedness in our state after every gate. And so the record for ion traps is actually an order of magnitude better than our gates. So this is a group at NIST and at Oxford have shown gates better than 99.9%. And we're sort of just about 99. And so the challenge, I would say, for ion traps is to combine these high fidelities with long chains, or with like a larger system. So people have shown very fast gates, sub-microsecond gates, and people have shown high fidelity gates, 99.9, and people have shown gates in large chains, up to 17 ions, okay? But not all of these things combined. So I think there is a perfect, we have one expert in the audience here, there's a perfect laser pulse solution out there somewhere, presumably, which is robust to these noise mechanisms that I showed, or that I mentioned, robust to intensity noise, frequency noise, and so on, fast and able to deal with multiple modes. And so this development is ongoing. But of course, there will be a limit at some point. At some point, there'll be probably more modes than you can deal with, even with a robust pulse sequence. And at that point, but I don't know where this is. I mean, I've drew like 10 here. It's certainly going to be more than 10. It's going to happen at some point, maybe around 50 or something. I can't really say. But there's a trade-off where you don't want to, have a pulse sequence designed that is robust for a gate in 50 ions. So you might want to have groups of maybe 30, 40, 50, and then connect them in this way. So I guess that's kind of the way forward in terms of the architecture. Yeah.
So this bars and stripes state preparation.
Yeah.
Can you use QAOA for doing that, or
Yes, I guess you could. That is true. If you do QAOA, you could probably reduce the number of parameters. That's probably your idea. Yeah, that's right. I think that's probably a way of doing this. Yeah. The idea here, I guess, is that the fact that this is bars and stripes is kind of artificial. There's no sort of physical system that corresponds to this, to this state as such. In the other cases, we start from a Hamiltonian, And here we're starting sort of from a, in a sense, arbitrary data set. It's kind of a toy optimization problem, if you like. And you're trying to get to this state by just doing these layers, single qubit layer, 2-qubit layer, and so on. And so that's kind of a different paradigm. But I agree with you. If you have a Hamiltonian that you can use that maybe doesn't have some of these terms in it, maybe you can do better. Yeah.
What are the timescales involved here, like a function of value?
Oh, yes. So a single qubit gate takes about 5 to 10 microseconds. A 2-qubit gate takes about 200 microseconds. And so you can see this is, the time scale of this whole thing is maybe half a millisecond. The limit for us, though, is not really this time. The limit for us is currently our controller, uploading data to our controller is kind of wasteful. But we know how to do that in principle. Just in practice, we spend a lot of time sending data over USB cable. But this is kind of a technical issue. The speed limit for ions, I would say, typical gate times are 100 microseconds for 2-qubit gates. But again, single, sub-microsecond gates have been shown, as I mentioned earlier. So the question is doing those in a large chain with high fidelity. But we are slower than a superconducting qubit system, that is true. And that'll also be the case for 1 microsecond gates. However, our coherence times are also very long.
Let's call it a day. Thank you.
Thank you.